So our next algorithm is insertion sort, and this basically works by swapping elements until you have your sorted list two at a time. So the way we do this is we first can take a for loop, or actually before we do any of that, we want to have the length of the array stored into a variable. So we can just pick n equals length, and let's just call this array. Okay, so now we take a for loop, and we want to do, so for I in range 1 to n minus 1. And the reason we do 1 here is because with insertion sort, we assume that the first element of the list is already sorted, so we don't touch it yet. So for the for loop, in the for loop, what we're going to want is a way to keep track of the indexes that we're going to compare and swap if needed. So we can set a variable k equal to array I. In addition to having k keep track of the current index we're on, we also want another variable to keep track of the previous index. So we can set another variable j equal to I minus 1. So always 1 before whatever index k is on. Next, we want to do our comparison and swap if needed. So the way we're going to do that is with a while loop. So while, and it's going to have two conditionals. One where j is greater than or equal to 0, because we want to always have a positive list index, because the negative one will not work. And we also need to check if k, which is our second index, is less than array of j. And if this is true, then we need to swap the elements. So the way we're going to do this is by setting the array of j plus 1 equal to the array of j. So after this, we need to decrement j. So j minus equals 1. And the reason for this is we're only going to enter this while loop until we find a number in the list that fulfills this requirement. So we need to keep going through the list until we find a value where k is less than an array of j. And once that happens, we swap, and then we exit our while loop, and we're going to have to do array of j plus 1. Let's rewrite that. 1 equals k. And this is essentially swapping the second element back to whatever we have stored in k. So to, I guess, visualize this better, the way it would work with this array is on our first pass, we would compare 10 and 9. And we would see that 9 is supposed to be less than 10. So we would rewrite our array as 9, 10, 11, 5. Next, we go to our second index, or start with the second index, and compare 10 to 11. And we see that 10 and 11 are the correct place because 10 is less than 11, so we never enter this while loop in the first place. Next, we would write the array again, 9, 10, 5. So now we compare 11 to 5, and we see that 5 is supposed to be less than 11. So what ends up happening is we will swap those two. So 9, 10, 5, 11. Same case will happen with 10 and 5. 5 is less than 10. So this will become 9, 5, 10, 11. And the same thing will happen with 9 and 5, because 5 is less than 9. So this will end up being 5, 9, 10, 11. And then eventually, even if you run this algorithm with this already sorted list, nothing will change and you'll end up with your answer.
So for selection sort, what we're going to be doing is taking each index and swapping it with the number that is the lowest out of everything in the array. So the way we do that is we'll take a for loop and we'll have an integer I equals 0, and it will have to be less than the length of the entire array. and then for each time it'll just increase by 1. And for each time you're going to make a minimum value equal I, and then what that does is that'll just have the index for that. So with the minimum being the index, what you're going to do now is just have another for loop, and this will be j, and this will be I plus 1, so it'll go through the rest of the list after this, and it will still have to be less than the length, and it will still increase by 1 every time. So what this is going to do is we're going to have an if statement, and if the value at the array at the index of j is less than the value of the array at the index, or the value at the index of the minimum, then what we're going to do there is take the minimum and make that be equal to whatever value j is at this point in the for loop. So after that, it will just go back to the original for loop, and if minimum has changed, it doesn't really matter here. It's just going to do the same thing every time. So it's going to make a temporary variable that is going to house the array of the minimum values index. So it'll hold that value there. And then what will be changed is the array at the minimum will become whatever I is. And then it's just going to swap here with the array at I becoming whatever the temporary variable is. And so that's it when it comes to the code for the program. So for visualization, it'll go to this 30, it'll swap it with the 7, so we'll have 7, 27, 35, and then 30. So then the second time around, it'll go from this point, and it won't be able to swap anything because this is the minimum value. So then it'll go to the next one, and then it'll just swap these two. So we'll be left with 7, 27, 30, and 35, compared to the original array that had 7 at the end. And the runtime for this whole entire algorithm is going to be O of n squared, because every single time, it doesn't really matter whether it's sorted or not, or if half of it is sorted, it's going to go through every element in the list, no matter what, and it's going to do a swap, which is going to be constant no matter what. So no matter what array you give it, it's always going to have the best and worst and average runtime of O of n squared.
Merge sort is a sorting algorithm where it recursively splits up an array into halves until it gets a bunch of subarrays, and then it compares the values and merges them back together into a sorted array. So we'll just start with our algorithm here. We'll define our function merge sort. And I guess it'll take our array. So let's define our middle index for the array to split it into halves with recursive formula. So we can define middle as the length of the array, and divide that by 2. We use a double slash to use the floor function. The left subarray is going to look like this. And the right subarray will look like this. And so now we can check if the subarrays are greater than a length of 1, then we'll recursively split those halves into more halves. We're gonna have a while loop to check if the values in each subarray half, like the left and right, should go, like which one of them should go into the sorted array based on which one's like less than the other. I equals j equals k equals 0. And so our while loop will be while I is less than length of left and j is less than length of right. If the current value in the length or in the left side is greater than the, or is less than the right side, then you just add the value from the left into the sorted array. So we have if left I is less than or equal to right j, we'll have array k equal to left I. And then after that, we'll increment I by 1 to go to the next value. And so if this is not the case, then we'll have an else in case the right value is actually less than the left value. So then we'll have array is equal to right j. And then we'll increment j by 1. And then after we do this, we'll increment k by 1 because then it's like the next value for the sorted array. And then for the leftover values in the array, after this while loop goes, we'll have while loops to add the rest of the values in left or right into the sorted array. So we'll have while left I, or while I is less than length of left, we'll add it to the array. So array k equal to left I, increment I by 1, increment k by 1. And then same thing for the right subarray. So now that we have that, the algorithm is, so for example, if our array is like 0, 3, to 1. First, we'll define the middle index as like here, so that would be 2, because the size is 4, and then divided by 2 is 2. So length of this is equal to 4, or 2. So as you can see, it like recursively merge sorts so that it divides each value in this array into its own subarray. So first it'll divide it into this and this, and then it will divide it again. So then after this, it checks if the left is less than or equal to the right, and it'll add that. And then if it's not the case, then it'll add the right one instead to like the return array. So this is the left and this is the right, and this is the left and this is the right for the other case, or the other loop or iteration. So it checks if 0 is less than or equal to 3, and it is, so then it adds 0 into the array. And then after that, it checks that 3 is left, so then it'll add 3 to the return array. And then same case with here, it sees that 1 is less than 2, so it'll add 1 to it, and then 2. So then we have these arrays, and now this is the left and this is the right. So then it looks at the first value in each of them, and it sees that 0 is less than 1, so it'll add 0 to the sorted array. And then it increments the index so that the next one it looks at for the left side is 3, and it's still looking at 1 for here. So then it looks and sees that 1 is less than 3, so then it'll add 1, and so on. So then it'll add 2, and then 3. And so now we're left with our sorted array. We're talking about time complexity of the algorithm. The algorithm splits the array into halves, n, or log n times. And then when the algorithm merges back together, it does that n amount of times. So where n is the size of the array. So judging from that, and also that it does this no matter the case. So like it always splits the array into halves and then merges them back together, meaning that the runtime for worst, best, and expected is always going to be O of log, or n log n.
All right, so I will be showing you how a quicksort algorithm works. So for an implementation of a quicksort algorithm, we can use two basic functions. We'll call these functions partition and quicksort. So these functions are going to take the same parameters, which is going to be array, the array we want to sort, left, which is the leftmost index, and right, which is the rightmost index. So these are our function definitions. We'll start with partition. So before we go any further, let me just write a sample array for everybody. So we'll say 7, 8, 2, 9, 5. You know what? Let's make this 9 a 4. So this is a 4. Okay. Now partition. The first thing we want to do with the quicksort function is define the rightmost index as our pivot. So we'll say pivot equals array right. Next, we want to define I, which is an index value, and we'll set it equal to left minus 1. So I, right now, if we were to put it, say, array I, we would be looking at 5 because left minus 1 would be the leftmost index minus 1, which takes us to 5. We're going to handle that in our for loop, which is obviously for the array traversal. So next we want a for loop for, we'll say j in range left, right. So for j, we want to check for each element that we're traversing over, we want to check if that element is less than or equal to 5. So we'll say if array j is less than or equal to pivot, because 5 is our pivot, we are going to first increment our I value. So we'll say I equals I plus 1. And then next we're going to swap the element at array I and the element at array j. So first let's write this in code and then pseudocode, and then we'll see what this is actually doing. So we'll say swap array I array j. All right, so what is this statement doing? It's saying, okay, if we stumble into an element that is less than 5, so we check 7, it's not less than 5. We check 8, it's not less than 5. We check 2, it is less than 5. Now we're going to do I equals I plus 1. So right now I is going to be -1. -1 plus 1 is 0. So I equals 0. We're going to swap array 0 with array j, which in this case is 2. So index 2. So we swap element 2 with element 7, which gives us the array 2, 8, 7, 4, 5. And this is our new array. Okay, what do we want to do next? Well, this loop is going to continue until we don't have any elements left except for the pivot. So we need to have one more swap outside of the for loop in order to handle the pivot. So we'll say swap array I plus 1 with array right, which array right is the pivot. And then lastly, we're going to return I plus 1. And this is for our quicksort function. We'll get into that shortly. So let's look at what we're doing right now. So we continue with our for loop until we run into 4, which is less than 5. And then we do another I plus 1. So at this point, I is 0. So I plus 1 becomes 1. So we're looking at 8. We're looking at 8 and 4. We'll swap those two, which gives us 2, 4, 7, 8, 5. At this point, there's the for loop breaks. We've gone through every element in the array, and there's no more elements that are less than 5. So we run our final swap statement, which is swap array I plus 1. So at this point, array is equal to, or sorry, I is equal to 1. 1 plus 1 is 2. So the element at index 2 is 7. So we swap 7 and the pivot, array right, 7 and 5, which gives us 2, 4, 5, 8, 7. Okay, so this is where we're at right now. 2, 4, 5, 8, 7. This array is clearly not sorted. That's why we need one more function. So this function is called quicksort. First thing we want to do is check if right is greater than left. And the reason we want to check this is because if right is not greater than left, then we don't need to run this function because there's nothing to sort. The only reason right would not be greater than left is if the array has like no elements in it, and both are, you know what I'm saying. So this is just to check if we want to run quicksort. So if it is the case, we do want to run quicksort. So now we need to pull this value, the I plus 1, which this is the partition index, we'll call it. So we'll say pi equals partition array left, right. All right, so our partition index. What is this? This is just saying what is the index of the pivot value. So the pivot value, the partition value, partition index we're calling it, is going to represent where we're subdividing the array for our sorts. So in this case, it's 2, so it's in position, index 2 on the array. And then we need to run some swaps. So, sorry, we're not going to run swaps. We're going to recursively call quicksort, which is going to run the partition and run the swaps for us. So we're going to call quicksort based on this partition index. So we want to check the left side of the array based on the partition index and the right side of the array. So the first thing we'll call is quicksort array. We're going to set left equal to left, right, the leftmost index, so 0, and then we're going to set right equal to pi minus 1. We don't care about the pivot value. We already handled that. We care about what's on the left side of the pivot value, so we set it equal to pi minus 1. So let's look at what this does really quick. So we have our 2, 4, 5, 8, 7. I'm going to write it again over here. We're only looking at 2 and 4 because we're looking at pi minus 1, which is 2 and 4. So we run quicksort. It's going to call it's going to call partition. And we're going to repeat this process. So 4 gets set to the pivot. For each element in the array, if there's a value where the pivot is greater than that value, which there is, 2 is less than the pivot value, we're going to swap those values. So now we have 4, 2, and then we break the for loop, and lastly we swap the pivot value with I plus 1, which in this case starts at -1, goes to 0, and then we add one more. I plus 1 makes it 1. So the element in index 1 is 2. The pivot element is 4, so it becomes 2, 4 again. And at this point, this segment of the array is sorted. Now we are going to have to handle the right side of the array. So we'll run quicksort again from the right side of the partition index. So we'll say array, we'll set left equal to pi plus 1 because we want to start from here. So pi plus 1, and then we'll say that the right side is just going to equal right, the rightmost index. And now this is going to handle similarly for 8 and 7. So we'll see 8, 7, sets the pivot to 7. There's no values less than 7, so the for loop doesn't do anything, and then we do a swap. I plus 1, negative 1 plus 1 is 0, so we swap 8 with 7, and we get 7, 8. Now, technically, this would run one more time. This would run until we have, this would run until we returned I plus 1 for everything. So I plus 1 here is going to return 4, and it's going to return 8, right? Because we set in this one, I plus 1 goes from negative 1 to 0, and then 0 plus 1 is 1. So the index at 1, or sorry, the element at index 1 is 4. So this would be a partition. And then in this one, the index is actually going to be 0. So it's going to be 7 because we never run this I plus 1. So it's just negative 1 plus 1, which is 0. So at this point, we would run within this quicksort call. We would run this again until what we have is this 2, 4, 5, 7, 8. And then at this point, we truly know that the array is sorted. So this would continue running until this is the case. And then in terms of time complexities, best case, it's going to be n log n. And the reason this is our best case is because we're using the partition to divide the arrays. So we have to compare less overall numbers. We don't have to continue comparing numbers that we've already seen if the partition value actually works like it should, because it's going to divide the array in half. So instead of comparing 2, 4, 8, 7, we're just comparing 2 and 4 and 8 and 7. The same thing would apply if the array was bigger. So we're reducing the overall number of calculations that we have to do, and thus reducing the time cost. Worst case occurs if we pick a bad partition. Worst case is n squared. This occurs if the partition is either the highest value in the array or the lowest value in the array. So for example, if we pick the rightmost index and the array is already sorted, then we're going to be dealing with worst case. Because let's say, for example, that this is 9. Well, there's every single index in the table is less than 9. So what's going to happen is we're going to have 7, 8, 2, 4 all on one side of the partition. And then on the other side of the partition, there's going to be no values at all. So we still have the cost of comparing 2, 8, 7, 4. We're still comparing 4 numbers against each other rather than 2 numbers against each other. So we're losing all the benefits of the algorithm if that's the case. And the average case is n log n. Because in just a random array, not sorted, we can assume that most of the time the rightmost element is going to be somewhere near the middle value-wise. It's not going to be perfectly in the middle. We can't assume that every time, but it's going to be somewhere near the middle, in which case the algorithm will still run efficiently in n log n time.